the young research scholars talk. We'll be having two research scholars. We'll start with Ms. Srijonee. She's from HRI and she's student of Professor Kalyan. And she'll be talking on a note on sums of squares in non-totally real fields and beyond. So Srijonee, over to you.
Good evening, everyone. Good evening, everyone. First, I would like to thank the organizer of ICCGNFRT for giving me this opportunity of presenting my work here. Today, I will give a survey kind of talk on sum of squares in mainly non-totally real fields. So the plan of my talk will go like that. First, I will give a brief introduction. Then I'll discuss on the development of the theory of sum of squares in non-totally real fields. After that, for proving my main theorem, I'll state some useful results. Then after the main theorem, I'll mention some results on real bi-quadratic fields. And then if the time permits, I'll try to share my thoughts about my next project here also. So let's start. The question, which integers can be written as sum of integer squares, is one of the fundamental questions in algebraic number theory, and it has a long and rich history. It has a long and rich history consisting of the works of Diophantine, Brahmagupta, and Varma's, Pales, etc. So in 1770, Lagrange proved his famous four-square theorem. We can say this is the formal beginning of this subject. In this theorem, he states that the sum of four squares, x square plus y square plus z square plus w square, this represents every positive integer. And after this theorem, many results in this area has been developed. One of the most famous generalization along this line is Waring's problem. It says that whether for every positive integer n, there exists an associated positive integer gn such that every positive integer can be written as sum of gn number of nth power of integers. On the other hand, in the early of the 20th century, Ramanujan extended Lagrange's result, and he proved that up to equivalence, there exists exactly 54 quaternary diagonal positive definite quadratic forms, which represents all positive integers. Later, Dickson extended these results to non-diagonal fields also. So after this theorem, the question arises that how can we extend these results to an algebraic number field? Before proceeding in this direction, I will first give two definitions here. First, the totally real field. Suppose K is an algebraic number field, means it is a finite degree extension over the field of rational number, and with degree n. If it has R1 number of real embeddings and R2 pairs of complex embeddings, then this implies that R1 plus 2 R2 equals to n. And we can say that this is totally real if it has no complex embedding, that is, if R1 equals to n. And if there exists any complex embedding, then we can say that the field is non-totally real. The examples of totally real and non-totally real fields are also here. So if we consider Q root 3, it is a real quadratic field and it is totally real because both embeddings are real. And if we consider the field Qi, this is non-totally real 2-degree field over Q, and its ring of integer is Zi, that is the Gaussian ring. And now we consider the totally positive number. What is totally positive number? A number alpha in a number field K is called totally positive if all the R1 conjugates are positive. That is, all conjugates are positive, then it is called a totally positive number. So now we'll focus on only non-total development of the theory of sum of squares only in non-totally real fields. So before proceeding in this direction, I'll also give another two definitions. First, the level of field and the ring of integer. Suppose K is a number field, then the level of a field is the minimal number of squares required to represent -1 as sum of squares. Similarly, we can define the level of the ring of integers also. Now we'll give the definition of the Pythagoras number in a broad setup actually. Suppose L is a commutative ring, and sum of A square is the set of elements in A which can be represented as sum of integer squares. Now the number Lx is the minimum number of squares required to represent x as sum of squares in A. It is called the length of x. If we take the supremum of length of x for all x in sum of A square, this is called the Pythagoras number of A. We can get the examples of levels and Pythagoras numbers in our following slides. So first we move to the complex quadratic cases. In 1970, Moser showed that for k equals to q root over minus d, where d is a positive square free integer, then the level of k is 1, 2, or 4, and it is dependent solely on d mod 8, that is only on the factor d mod 8. And he also proved that the level of the ring of integers of k is 1, 2, 3, or 4, depending on d mod 8 and the norm of the units in k. After that, in 1983, Estes and Hasia showed that in which complex quadratic fields, every algebraic integer can be written as sum of 3 integer squares. He classified all these fields in complex quadratic fields. And in 2006, Zhiwang Zhu described which integers can be written as sum of 3 squares over arbitrary imaginary quadratic fields. Similarly, Wei described which integers can be written as sum of 2 squares over certain imaginary quadratic fields. As far as I know, there exist no results on Pythagoras number in complex quadratic field. And there is, I think there is some relation between level and Pythagoras number in imaginary quadratic field also, but no results have been found till now. So now we move to the bi-quadratic cases. In 2014, Gang and Z showed that for a field k equals to q root over minus m minus n, for distinct positive square free integers m congruent incongruent 3 mod 4, then every algebraic integer can be written as sum of integer squares, and if among them in some fields the level of OK is 2, then we can say that its Pythagoras number is 3. As far as I know, there is no result. There is no result on sum of squares in complex biquadratic fields except this one, and we can form some questions. Number 1, for any complex biquadratic field k, what is the level of k and OK? And for quadratic fields, complex quadratic fields, Moser have proved the result for complex quadratic fields, but biquadratic one, there is no result. And what are the Pythagoras number of OK in these fields? From Peter's result, we know that the Pythagoras number's upper bound is 5, but what is the exact number? We don't know. Also, the problems solved by Estes and Hasia, Ziwang, Zhu, and Wei for complex quadratic fields can also be done for biquadratic one. Now I move to the cyclotomic fields. In 1971, Moser proved that for k equals to q zeta, where zeta is a primitive nth root of unity, then the level of k is 2 or 4 depending on n. And from the work of Z and Wei, it is described that which algebraic integers in a cyclotomic field can be written as sum of integral squares, and among them, which are expressible as sum of 3 integral squares. They have also proved in the same paper that the Pythagoras number of a cyclotomic field is 3 or 4, depending on n mod 4. Now, I'll state some useful results for proving my main theorem here. Number one, that is Artin-Schreier theorem in 1965. In this theorem, it is stated that if C is algebraically closed with a subfield F, such that C is a finite degree extension over F, then the C equals to F of is a quadratic extension over F, and it has characteristic 0. Moreover, if A is any non-zero element in F, then exactly one of A and minus A is a square in F. And the second theorem is the Ludwig-Dress theorem in 1982. Suppose K is a field of finite level, then all subrings R of K with quotient field K have finite level if and only if K is of positive characteristic or K is algebraic over Q. It means if K is a non-totally real field, then from these two theorems, we can say that it has a finite level, and its ring of integer. From the second theorem, we can conclude that its ring of integer also have the finite level. Using these two theorems, we have proved our main theorem. I'm just stating this theorem here. Suppose K is a non-totally real field and OK be the ring of integer of K, then every algebraic integer in K multiplied by 4 can be written as sum of 5 integral squares. And now I will mention some results on totally real biquadratic fields, which I have arrived which I have got recently, actually. The post from first I want to tell from where the question arises. In 2020, Vitakala and Yatsina have proved that for quadratic field K equals to Q root T, there exists integer S such that every positive integer multiplied by S cannot be represented by sum of integer squares. And they have given an upper bound of this S. Also, they have given a lower bound of S such that every totally positive integer multiplied by kappa S can be written as sum of 5 integers, where kappa is 1 if D congruent 1 mod 4 and kappa is 2 if D congruent 2 or 3 mod 4. So we have tried to extend this result to to real biquadratic field. Here our theorem, first theorem, which tells that if K is a Q root over minus M root over M root over N be a real biquadratic field where M and N are two positive square free integers and R equals to Mn by GCD of Mn square, then for every real biquadratic field K, there exists a positive integer M0 depending on Mn and R such that there for any integer S less or equals to S0, every element of S multiplied by a totally positive integer cannot be written as sum of integer squares. In theorem 2, we have proved that there exists positive integer S, and we have found a lower bound of S, that is S greater than equals to S0, then every totally positive integer multiplied by S can be written as diagonal quadratic form in K with coefficient 1 and minus 1. That is sum of integer squares minus sum of integer squares in this form. And in theorem 3, we have tried to give a minimal polynomial, which is an if and only if condition. If the minimal condition is satisfied, then every totally positive element can be written as product of two totally positive integer in the field K, where K is the same field. Now, I want to talk about my next project. Actually, there exists a clear classification of all indecomposable integers in quadratic field. They're depending on continued fraction and the semi-group structure. But in complex biquadratic, in real biquadratic field, there exist very few results on indecomposable integers. So I want to extend the results to the biquadratic cases, and the existing works on biquadratic case and quadratic case for indecomposable integers are here. And also on the sum of squares, I have till now I have worked on sum of squares in some number fields. I want to extend this work to any commutative ring also. Here are some relevant works. So here are the references of my talk. And